The last part we're going to do for problem solving and data analysis is probability. So it starts about 1/3 the way down on page 15. So we're going to start with theoretical probability. For that we've got some definitions. It says any occurrence for which the outcome is uncertain is called an experiment. Example, you toss a coin. The outcome would be heads up, which we normally denote as H, or tails up, which we would denote as T. Number 2, the set of all possible outcomes of an example is a sample space of the experiment, denoted by S. Okay, so once we've done the experiment, we could note or write down every single outcome. Okay, this isn't the outcome that we got on the experiment, but it would be the possible outcomes. So the example of the sample space of tossing a coin would be HT. The sample space of rolling a single dice would be 1, 2, 3, 4, 5, or 6. And then number 3, an event denoted by E is any subset of the sample space. So an event in this example would be just T. It's just one example of something in the sample space. Okay, so bottom of page 15, we're actually going to move on to finding probabilities. We're going to start with theoretical probabilities. So it says, and if an event E has N of E equally likely outcomes in its sample space and N of S equally likely outcomes, the theoretical probability of event E is P of E equals the number of outcomes in event E divided by the total number of outcomes. This is pretty wordy, but really all this means is the denominator is going to be the number in your sample space. Okay, so how many total outcomes do we have? Okay, the numerator is going to be how many of those outcomes make the probability that we're trying to find. Okay, so I think the examples will clear up this definition. Bottom of page 15, it says you toss a fair coin. What is the probability of a coin landing heads up? Okay, so I'm going to go ahead and write out the sample space. I'll do this for a couple, and then we'll move on from that. We don't have to do this work later. The sample space of tossing one coin is heads or tails. Okay, so the probability of landing heads up, so the probability of H. The denominator is how many are in our sample space, which is 1, 2. Okay, and then the numerator is the event in the sample space that makes this probability true. Okay, so we're finding the probability of landing heads up. The only event that would make that true would be H, so the probability would be 1 or 1/2. Okay, I'm going to go ahead and do that again for a couple more on page 16, and then we'll stop just doing the work. We should be able to figure this out just by talking through it. Okay, it says a dice is rolled. Find the probability of rolling a 3. Okay, so I'm going to write the sample space out over here. When you roll one dice, it's 1, 2, 3, 4, 5, 6. Those are our possible outcomes. Okay, so for every single one of these, our denominator is going to be 1, 2, 3, 4, 5, 6. Okay, so the probability of rolling a 3, which I'm just going to denote P of 3, is going to be, okay, out of this sample space, how many are 3s? Okay, that's just going to be the number 3. So we have 1 here. Okay, so the numerator is 1, the number, or no, sample space was 6. Okay, number 2, we want the probability of rolling an even number, which I'm going to denote as capital E. Okay, so we need to find the number in our sample space that makes this true, an even number. That would be 2, 4, 6. So we have 3, and total in our sample space was 6, which reduces to 1/2. Okay, a number less than 5. I'm just going to do P. I'm just going to name this A here. Less than 5, that would be 1, 2, 3, and 4. Okay, we don't include 5 because it doesn't say less than or equal to 5. Okay, so that's just 4 there. And again, our number in our sample space is 6, so this would reduce to 2/3. Okay, number 4, a number less than 10. If you look in our sample space, that's 1, 2, 3, 4, 5, 6. Okay, so I'm going to name this maybe B since I've already used A. We have 6 that are less than 10 out of 6 total. That is 1. Okay, middle of page 16. We're going to keep doing these theoretical probabilities. It says you are dealt one card from a standard 52 card deck. find the probability of being dealt. Okay, let's just quickly go over a 52 card deck. There are hearts, we have spades, clubs, and what is the last one? Diamonds. Okay, so you have 4 sets. There's 13 each of those. And then you have the numbers 2, 3, 4, 5, 6, 7, all the way to 10. And then you have jack, kings, and queens of those. Okay, so there's 4 twos, there's 4 threes, because you have a diamond, a spade, a heart, and a club of each of those. Okay, so I'm not going to write out that whole sample space. That would be 50. I would have to write out 52, which we don't really need to do. Okay, so we want to do number 1, the probability of a king. Okay, so we have to think how many kings are there. There are 4. There's the 4 of hearts, the 4 of spades, 4 of diamonds, and 4 of clubs, out of 52 cards total. Okay, that actually reduces to 1 over 13. Number 2, a heart. Okay, so we have 13 hearts. So you have the jack, the king, the queen, the 10, the 9, the 8. Okay, so the probability of a heart, you have 13 hearts, and there's 52 total, which reduces to 1/4. Okay, and then the probability, I'm going to do KH for king of hearts. Okay, how many king of hearts are there? There's actually just 1, and that's out of 52 cards total. Okay, one more on page 17, top of page 17. We have a red card. Okay, so probability of reds. We really have to think this one through. The denominator is going to be 52. There's 52 total cards. How many red cards? Well, we have diamonds and hearts are red. There's 13 diamonds, and then there's 13 hearts. So we'd have 26 red cards, which reduces to 1/2. Okay, the other half would be black cards. Okay, moving on to empirical probability. Okay, empirical probability applies to situations in which we observe how frequently an event occurs. The empirical probability of an event E is probability of E equals observed number of times E occurs divided by the total number of observed occurrences. Okay, so before we move on to the examples, I want to just do a quick example of what we mean by this. We know that the probability of rolling a heads up in a fair coin is 1/2. We figured that out. Okay, this is theoretical. I'm just going to write that. Okay, that's our theoretical probability. That's what should happen. Okay, that's in theory. The probability of flipping a coin and getting heads up is 1/2. Okay, but let's say you actually do an experiment and you flip a coin 10 times. Let's say you get heads, tails, tails, heads, 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 tails, 1, 2, 3, 4, 5, 6, 7, tails, tails, 1, 2, 3, 4, 5, 6, 7, 8, 9 heads. Okay, I'm just making those up. Okay, so let's say you flip a coin 10 times. These are your results. Okay, then the empirical probability of rolling a heads up would be 1, 2, 3, 4, 5. Actually, let's change this last one to tails. Okay, just because this doesn't always happen in real life. So the empirical probability would be 1, 2, 3, 4 heads out of 10. Okay, which is 2/5, which isn't quite 1/2. So this would be empirical probability. Okay, so this is actually going out and doing the data yourself, and this is the raw data probability. Okay, example, it says among 2,039 marbles in a container, 548 are blue. What is the probability of picking a blue marble from the container? Okay, so we want to do the probability of blue. Okay, total marbles, there's 2,039, so that's going to be our denominator. That's how many experiments or how many marbles we have. And then the probability of it being blue would be however many are blue, so 548. As a decimal, let's go ahead and divide that out, just because I'm not really sure if this number is large or small. It's approximately 0.27. So about a 27% chance you would pick a blue marble. Okay, bottom of page 17, it says in 2007 there were approximately 235.8 million Americans ages 18 or older. The below table shows the distribution by marital status and gender of this population given in millions. Okay, let's go ahead and go through this table before we look at the example. Okay, so males. Okay, so just going through the males, these are Americans. There's 37.5 million never married, 64.7 million married, 2.7 widowed, 9.6 million divorced, and then there's total 114.5 million men. Female the same way. So you can go through never married, married, widowed, divorced, then you have 121.3 total women. Okay, and here's just totals at the bottom here. So there are 69.2 million people or Americans never married, 129.9 Americans married, 13.9 Americans widowed, 22.8 Americans divorced, and then total Americans we have 235.8. This is Americans ages 18 or older. Okay, if you check these should add up. Okay, so if you add those two, you get this one. Add those two, you get this one. Okay, so it says if one person is randomly selected, find the probability that the person, number one, is divorced. Okay, so we'll do probability of divorced. Okay, first of all, the bottom number is our total, so 235.8, and this is in millions. Okay, we can leave off the millions since all of these numbers are in millions. Okay, and then we need total divorced. Okay, so total divorced would be 22.8. Okay, again, I'm going to go ahead and put this in decimal form so these numbers mean more. It's about 0.097. So a 9.7% chance that person will be divorced. Okay, number two is female. Okay, so again, the bottom number needs to be 235.8, and this is in millions. Now we need the probability of female, so total females would be 121.3. Okay, I'm going to go ahead and put this in decimal form. This should be about half, okay, because about half of Americans are female, about half are male. We get about 0.51, so about a 51% chance. If you pick one person out of this group, it's going to be female, which makes sense. Okay, top of page 18, we're looking at number 3, has never been married, which I'm going to go ahead and leave out this table here. So I'm going to do probability of N for never been married. Again, the total is at the bottom. Okay, and then never been married, total is 69.2. Okay, so 69.2 divided by 235.8, got about 0.29. It's about a 29% chance if you pick one person, they've never been married. And then number 4 is male, so this would be probability of male. So 235.8 on the bottom, and then total men, we have 114.5. Okay, again, this should be about 50%, which I got about 0.49. So about a 49% chance if you pick one person out of this group, it's going to be male. Okay, and then the last thing we're going to learn in this section is conditional probability. Okay, which there will be some like this on the exam. Okay, definition, it says the probability of event B, assuming that the event A has already occurred, is called conditional probability of B, given A. The probability is denoted by, we do probability of B, and then this line represents given A. Okay, so how do we solve these? It says think of the conditional probability as the probability that event B occurs if the sample space is restricted to the outcomes associated with event A. Okay, so for example, we could say, what's the probability of drawing a king of hearts given that the card you drew was red? Okay, so we would restrict to just red cards. Okay, so for conditional probability, our denominator isn't the total anymore. It's going to be the total of what the given is. Okay, so example, it says a letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a vowel given that the letter chosen comes before J. Okay, so if we were just given this, a letter is randomly selected from the letters of the English alphabet, find the probability that the letter chosen comes before J. We would have that the denominator is, 26? However many letters there are in the alphabet, and then we would count how many come before J. But we have a given, okay? So we want the probability, this would say find the probability of selecting a vowel. So we count the vowels, and then our denominator would be 26. Okay, so we want the probability of selecting a vowel given it comes before J, which I'm just going to denote by J. Okay, so let's go ahead and do some counting here. Let's look at how many vowels there are. So we have A, E, I, O, U. Okay, so we can't fill this in yet. And then the letters that come before J. So A, B, C, D, E, F, G, H, I, and we can't count J. Okay, so our denominator becomes however many this is associated with, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now our numerator is not how many we have here, 1, 2, 3, 4, 5, okay, because we're given that the numerator has to be in one of these. Okay, so our numerator is going to be the vowels restricted to this. Okay, so we have an A, and we have an E, and we have an I. We don't have an O, we don't have a U in this new sample space. Okay, so this would be 3/9, which is 1/3. Okay, so this is a little confusing. I think it helps to write it out. And you have to remember that the denominator changes. You have a new sample space. Then you figure out your numerator given that new sample space. Okay, bottom of page 18, it says find the probability of getting a heart. So probability of a heart given that the card you have is red. Okay, so our denominator is how many red cards there are. Okay, so we decided that there were 26 red cards, which I'm going to write a note in here so when you look back to study, you'll see that there are 26 red cards. Okay, and then how many of those red cards are hearts? That would be 13. Okay, so I'm going to put 13 red cards are hearts. Okay, which that actually reduces to 1/2. Okay, bottom of page 18 says find the probability of getting a black card given that the card you were dealt is a spade. Okay, so first of all we need to restrict our denominator. There are 13 spades. Okay, so I'm going to write that again. So 13 spades. Okay, how many of those spades are black? Okay, they're actually all 13. Okay, because all of your spades are black. Okay, so I'm going to put 13 spades are black. Okay, which is 1. Okay, so if you were gambling and someone said, I drew a card and it's a spade, what's the probability that it was black? You could say it's 100%. Okay, and then one more page, we're just going to do one more table type problem. Okay, so page 19. Okay, it says the table below is based on 100,000 women in the U.S. ages 40 to 50 who participated in a mammography screening. Okay, so again, we're going to read this table. Positive mammogram. So these women went in, they had a positive mammogram. Okay, 720 of those had breast cancer. 6,944 did not have breast cancer. And here's the total of positive mammograms. Negative mammograms, 80 had breast cancer. 92,256 did not have breast cancer. And then there's the total for negative mammograms. And here's the total for breast cancer, no breast cancer. And then this is the total of women, which would be 100,000. So that's going to be our denominator if we do not have conditional probabilities. Okay, so number 1, it says find the probability that a woman has a positive mammogram given that she does not have breast cancer. Okay, so this one's a given, so our denominator will not be 100,000. So we have a positive mammogram given that she does not have breast cancer. So I'm going to just do NB for no breast cancer. Okay, so the denominator is how many we have in this no breast cancer. Okay, so the denominator is going to be 99,200. Okay, that's our total for no breast cancer. Okay, and our numerator is how many of those 99,200 had a positive mammogram. Okay, so that would be 6,944. Okay, so again, I'm going to explain this again. How many of those that had no breast cancer had a positive mammogram? Okay, if you divide that out, so I'm going to go ahead and do that, 6,944. Get about 0.07. Okay, and then number 2, find the probability that a woman has no breast cancer given that she has a negative mammogram. Okay, so probability that she has no breast cancer given that she has a negative mammogram. Okay, so first our denominator is going to be negative mammogram, which the total for that is 92,336. Okay, and out of those 92,336, which just would be these two numbers, how many did not have breast cancer? That would be 92,256. Okay, and if we divide that out, we get about a 90.99, so 99% chance that will happen. Okay, so ending probability ends the problem solving and data analysis section. You can go ahead and stop there and practice set